All right, Tegrity is on. She can hear me, I think, right? Okay, that's better. All right, so let's walk through a one-way ANOVA with a really nice example. And a lot of you, not in the last article critique about yoga, but the one about school performance, a lot of you brought up the effect that sleep would have on school performance. So this kind of dovetails nicely with that. So we'll use that as an example to walk through ANOVA. So let's say we're looking at a sample of high school students, right? We want to know if hours of sleep differs for each grade level, right? So basically we're asking, do hours of sleep vary across high school, or do the hours of sleep students get at night? Does this depend on grade, right? On whether they're freshmen, sophomores, juniors, or seniors? So this is our question. So if this is our question, does hours of sleep differ between students in different high school grades? What is our independent variable in this one? Hours of sleep. Actually, no. Okay, so independent variable is actually the grade, right? Because we think grade is influencing hours of sleep. So it's a little backward sounding. So the independent variable is grade. We think that grade is influencing the number of hours you get at sleep at night. And so if grade is our independent variable, then what is the level of that independent variable? Like, is it nominal, ordinal? Yeah, it's a little confusing. So basically, it could be nominal. In this case, it's ordinal because we can do some kind of ranking here, right? We could say freshmen smallest and seniors tallest, older. So we can rank these young to old. So an ANOVA can use nominal, where there isn't really a ranking, but it can also look at these ordinal differences as well. And when we do the lab tonight, the variable you'll be using is an ordinal level variable. But it's still like a grouping variable, right? It's just a group that we can order. So if this is our independent variable, then what's our dependent variable? Right, hours of sleep. And what level is this? Right? And in fact, it's a ratio if we want to get really specific, because 0 is meaningful. Like, a lot of us know what it's like to get 0 hours of sleep. Hopefully not anymore, but we know that. So this is our question. And to answer it, let's say we survey a sample of 10 students in each grade, right? So we get 10 freshmen, sophomore, juniors, and seniors. So we have 40 students total, 10 in each grade. And so here's kind of our data, right? It's a little average of our data. So you can see the average answer for each grade here. And you can even kind of see a trend in that answer. Does anybody want to describe, like, is there a specific trend that kind of jumps out at you? Yeah, it's kind of weird. Like it like does mountains almost, right? Where it's like, or I guess valleys. But right, like it kind of varies, but a trend you could kind of see is that freshmen get the most, seniors get the least, right? And so we can see that difference here. But as usual, like as every test we've gone through in the last couple classes, we can see these group differences. But we want to know if these are differences that are reflective of differences in the population, right? Are they significantly different? Or are these just due to random variation in the sample that we got? Like maybe we got a group of freshmen who sleep a lot, and maybe we randomly got a group of seniors who don't sleep that much at all. So we need to test this against our level of significance. Against our p-value to see if this is a significant difference, right? So our question is, are these differences between hours of sleep for high school grades, are these significant, statistically significant? And so to test the differences between these multiple groups, we do this one-way ANOVA, and that will tell us if these groups differ significantly, right? Because if we just wanted to see if they differ, we just get the means. But if we want to see if they differ significantly, we want to test it, that's when we have to do this ANOVA. So again, this is kind of similar to an independent samples t-test so far, right? We're just looking at differences between groups. We've got our means. We want to see if they are significantly different. Here's where we start to see a bit of the difference. So in a t-test, we're only comparing two groups. The p-value will tell us whether or not the two groups differ, right? In a one-way ANOVA, we're comparing multiple groups, right? So the p-value will tell us whether or not there's a significant difference between any of the groups, right? Does any group differ significantly from any other group? So if we put this in terms of like null hypothesis significance testing, in an ANOVA, our null hypothesis is that there's no difference between any of these groups, that all these groups are roughly equal. So you can see this H naught is what the O is, but you can say HO too if you want to. But our null hypothesis is that all the groups are roughly similar. They're all about the same. Our alternative hypothesis is just not that. So it's basically, is there some difference? We think there's some difference between these groups. And so this means for the ANOVA test, we're not testing whether one group is different from the other. We're looking at whether there is a difference in any of these groups, right? So basically we're seeing whether all the groups are not the same. That's it. And so, yeah, we're just saying we think that these groups are not all equal, right? So they're not all equal. But it could be that one group differs from all the other groups. It could be that two groups are different from everybody else. It could be every group is different. You don't know. So basically, when you do an ANOVA, this is what your hypothesis is. And it could be any, the alternative hypothesis could be any of those. And so whenever you do an ANOVA, whenever you're comparing multiple groups, you have to do this ANOVA test first. Because you're basically asking, is any group different from any other group? And the reason you have to do this huge ANOVA to test for these group differences, the reason you can't just do like a t-test between freshmen and sophomore, and then freshmen and then, juniors, freshmen and seniors. The reason you have to do this one huge test that says, is there any difference, has to do with controlling for type 1 error. So you don't have to know tons about this, but just so you know why we do this more complicated test whenever we do this, look at multiple group differences, is when you do multiple tests on the same sample over and over and over again, you inflate your alpha level. You inflate your type 1 error, and you don't know it. You don't know you're doing it. So you could get a test, one of the 15 tests that you do, like if you're comparing individually like freshman to sophomore, freshman to junior, freshman to senior, every time you do that, you're inflating your alpha level. And so you might get a test back and it'll say that it's less than 0.05, but in reality, it's actually like 0.15 and you don't know it. So it's weird. It inflates your alpha, and this does all the tests at once, so it controls for that. And so you are not inflating your error when you do it. We'll talk about this again at the very end, but just so you know why we're doing this, this is why. But basically, anytime you compare more than two groups, you might hypothesize that one group's higher than another. You might have a reason to believe that you have a specific relationship that you're interested in investigating. You might think, I think seniors get less sleep than freshmen. I think they're busier. I think they have a lot of activities. There's good reason for me to think they're sleeping less. You might think that, and you can test that later. There's other tests that we do after this to see where the differences are. But the first thing you have to do is this test. So before you can pass go and look at specific differences, you have to look at this ANOVA and to see if there's even one difference. If there's any significant difference between any of the groups. So you have to show that the group means are not roughly equal, right? That they're not all equal. And then once you do that, you can kind of pass go and see which ones are different. And so this is what ANOVA will do. It will tell you if they're different. And once we know that, once we've got some support for this alternative hypothesis, then we can look more specifically at group differences. So first we have to look at whether there's support for this alternative hypothesis. And I also would like to mention at this point that if there wasn't any difference, right, if the null hypothesis was supported, then that would tell you that all the groups are about the same, right? So you wouldn't have to look specifically at which groups are different. You could just be like, oh, they're all about the same. I'm done with my analysis. It's over. There's no differences. I can walk away. So yeah, if there is a difference, that's when you want to look closer and see where that is. So this is the question we're trying to answer with a one-way ANOVA. Is any group different from any other group? That's our first question. And how we go about doing this, as your book says, when we do a one-way ANOVA, what we're doing is we're dividing up the variance in the dependent variable into two components. So we're looking at the variance, we're estimating the variance attributable to between group differences and the variance attributable to within group differences. I will talk a lot more about this, but that's basically what we're doing. We're going to talk about each of these types of variance now. So in our high school sample, right, what's our dependent variable again? Sleep, right? We think sleep depends on grade you're in. So we think the amount of sleep you get at night depends on the grade that you're in. And as we talked about before, every variable we have will vary. That's kind of like why they have their name, right? They vary. So we have sleep scores for each grade. You can see them there, right? We have our mean sleep scores. And each of these scores will vary, right? So for example, we have our freshman group, and we know there's variability in those sleep scores, right? Not all of them will be the same. So we have our average hours of sleep for the freshmen, right? We've got our 10 freshmen. On average, they sleep 7.8 hours a night, but not every student in this group has a value of 7.8, right? Some are lower than that, some get more sleep than that, and the scores average out to 7.8. So this variable varies. Our dependent variable varies within our freshman group, right? They don't all have the same scores. And this is the same for the sophomores, the juniors, and our seniors. So we have these four groups. We have the average score, but we know that there's variation around that score. And so this variability in the scores for freshmen, for sophomore, for juniors, for seniors, for all these groups separately, this is what we call within group variance. It's looking at within group differences. And so each group will have this variability. So each group, the freshmen, the sophomores, the juniors, the seniors, each will have some variability within their scores within the group. And so this is within group variability, and we're familiar with this. We've talked about this before. We've calculated it before when we looked at our variance estimates and we got our standard deviations. So within group variability is kind of familiar to us. Now we're just looking at multiple aspects of that, right? So instead of looking at it in one group, we're looking at it in four groups. The new piece of information for ANOVA comes with this between group variance, or these between group differences. So I want to talk about that a tiny bit too. So we already know scores vary within groups. We've been talking about that. But we also think that scores are going to vary between groups, right? So we think that perhaps freshman scores, although they vary within their freshman group, we think that freshman scores are going to be more similar to one another, right, to other freshman scores than to like sophomore scores or juniors or senior scores. This is essentially what we're saying when we ask that question, do hours of sleep depend on grade? We're saying that we know there's going to be variability within grades, but we want to know if the scores, if hours of sleep, if this is more similar within the groups than between the groups. So we want to know if freshman scores are more similar to each other than to sophomore or junior or senior scores. We want to know if sophomore scores are more similar to other sophomore scores than freshman, junior, senior, and on and on and on, right? And so to answer this, to get this kind of between group variance, to get that we have to compare each group mean against a grand mean. And so the grand mean is the mean of all the means. So it's like you take all the means, you add them up, and you divide them by the number of means. So it's the grand mean. You can also get the same exact score if you take everybody's score, add them up, and divide them by the number of scores. So the grand mean is just the mean for everybody in the sample. So it's the mean of the 40 participants. So we take the mean for each group, we get the average of the means, we see whether any group mean is statistically different from this grand mean that represents the average of all the group means. So we'll walk through this some more in the next couple slides. But this is really what we're trying to find out in ANOVA, right? Is this within group variability smaller than between group variability, right? If the variability within the groups is smaller than the variability between the groups, then we're basically saying that participants in each group are more similar to each other than they are to other people in the sample, right? We're saying group membership matters because the scores in the group are more similar. There's less variability in the scores within a group than there is with the group and the rest of the sample. So that's basically what we're asking. If the variability within groups is not smaller than the variability between the groups, right? So like if sleeping scores of the members of like freshmen are not more similar to each other than to members of the rest of the sample, then what is that saying? Like if freshman scores are not similar to each other, they're similar to everybody in the sample. It's basically saying that group membership doesn't matter, right? I mean, if your freshman score is not any closer to any other freshman score than to a senior score, we're basically saying there's really no effect of grade on sleeping. So if we see this, then we're saying group membership doesn't matter. Our sleeping scores don't systematically vary according to grade, right? They vary. Everybody has different sleep scores. It doesn't systematically vary within grades. So this is the question that we're asking with ANOVA. Does grade matter, right? That's basically what we're saying. Is the variability within the group smaller than the variability between the groups? Or are the participants in one group more similar to each other than they are to the rest of the people in the sample? That's our question. And to answer it, we have to get these values, right? So we have to get an estimate of within group variability. We have to get an estimate of between group variability. And then we have to see how these compare to each other, right? So we have to see if between group variability is bigger than within group, or if within group variability is smaller than between group. So we're basically going to get a ratio of these two levels of, or these two types of variability. All right, so the bad news is that to do this, we have to do these calculations. Like we have to get these variance estimates. So we're going to walk through them as a group. I will never expect you to do these again. But I think when we go through them thoroughly, you'll see what each of these is getting, how it's getting it. And then when you interpret your output, you have a really good idea of what that output means. So yeah, so the bad news is we have to walk through all of these. The good news is from here on out, SPSS will do it for you. And the other good news is that some of this is very familiar because this is very similar to calculating variance. We're just going to do it with kind of a different scope, right? So one of the variances that we have to get is for each group mean. And then the next variance we have to get is the each group mean in terms of the rest of the whole sample. So we have to get the within group and the between group variances. So to compare these different types of variability, we have to get them. And just like we found the variance around the mean way back a few classes ago, right, we just need to use the sum of squared deviations from the mean. Because if we just sum the deviations, we get a value of 0. So we have to square them so that we get rid of these negative numbers and we can add these all up. But we're basically just getting two different variance estimates, two different sums of squared errors. And we're going to be getting the sum of squares within and the sum of squares between. So we're looking at variance within our groups and we're looking at variance between our groups to see which one is bigger. So let's talk about this sum of squares within first. And sadly, they don't call it SSW, they call it SSE. So SSE stands for sums of squared error, which is the sum of squares within. But nicely, the next one we look at is SSB, so you'll know that's between. So basically SSB is between, SSE is the other one, so it's within. So this sum of squared error, this is close to our typical or our kind of familiar idea of variance. It's how each score within a sample group deviates from the mean of the sample group. So it's basically how each freshman score deviates from the mean of freshman scores, how each sophomore score deviates from the mean of sophomore scores, etc. So when you look at this equation, I put this variance equation up there so that you can kind of contrast it to what we've been doing in the whole class when we look at variance, or how scores are spread around the mean, right? This is our formula for variance. That's basically what we're doing, but we're doing it for each group, right? So this x of 1 means the mean of the first group. This x bar of 2 is the mean of the second group. X bar of 3 is the mean of the third group. X bar of 4 is the mean of the fourth group, right? So basically what we're doing is we're taking all the freshmen in group 1, and we're taking each freshman score and subtracting from it the mean of the freshman scores, right? And then we're squaring it. And then we do the same exact thing for the sophomores. We do the same exact thing for the juniors. We do the same thing for the seniors. So we're getting the variance for each of these groups. And the big thing is, so we're getting the variance. That's basically what we're doing here. We're not dividing by n minus 1. We're just getting the sums of squared errors. That's what we're doing. So we're getting the error, and then we're squaring it, and then we're summing it up, right? So we're basically getting the variance without dividing by n minus 1. We're getting the variance for each group separately. And then, because we have the variances for each group separately, but we want one value that describes the variability within all the groups, for all the groups in our sample, we add the variances together. So we're summing them up, and then we're adding them all together. So you're basically getting the variance for each group separately. You're not dividing it by n minus 1, but you're getting that sum of squares value, and then you're adding it all together. Does that make sense? So that's one of your estimates. So this SSE, the sums of squared error, the sums of squared of the error within groups, this tells us the entire amount of variability around the score in our sample that's due to variation within our sample groups. So this is the total amount of variability for the 40 people in our sample. How much of it has to do with these groups? This is that number. This is the amount of variability that's due to within groups. Does that make sense? So it's if we're asking how much do freshman scores vary around other freshman scores, how much variability is within that freshman group, how much variability is within that sophomore group, how much variability is within that junior group, how much variability is within that senior group all together. How much variability is there within groups? This is that estimate.
Does it give you 4 answers? Or?
So as you do this equation, you'll see you get these 4 answers, and then you sum them up. And you get one big answer that says all of the variability in the sample that's within any group, this is that variability. So it's
going to be the same within each group then?
It'll be different because, like, if you look here, let me see, we have different means. Right? So when you're doing this equation, you are saying the 10 freshmen, you're subtracting this first score. Let's say the first freshman has a score of 8 minus the mean, which is 7.8. And then the second freshman has a score of like 7 minus 7.8. And then let's say the third freshman has a score of 6 minus 7.8. You're going to do that for each freshman. Then you're going to sum all of those up, right? You're going to square them, and then you're going to sum them all up.
Okay, so these 4 sections are representing, say, just freshmen.
Right, so this one is just freshmen.
So it's not freshman, sophomore, junior, senior.
Well, so this one is just freshmen.
Okay.
Then this one is sophomore.
Oh.
So basically, like, this is for all 10 freshmen. For each freshman, you're going to do this, their score minus the mean. Then the next freshman, this score minus the mean, and then square it. And this score minus the mean, and then square it. So you're going to do that 10 times for each freshman, right? So like if we wrote out this whole equation, there would be like 40 of these. So we're basically just using this to stand in for every equation that you would do. So here's your 10. So this is X. The X is for those freshman scores. So you'll do this 10 times. Every freshman score, you would do this. You take it minus the mean of freshman scores only, because you're just looking at how much they vary within that group of freshmen. And then you'll square it. And then you'll do that for freshman number 2, minus freshman mean, square it. Freshman score number 3, minus freshman mean, square it. Freshman score number 4, minus freshman mean, square it. On and on until freshman score number 10, minus freshman mean, square it. Now you got those 10 squared deviations, right? So these are, the deviations are each person's score minus the mean score squared. You've got squared deviations for all 10 freshman scores, then you add them up. So then here is the number for all 10 freshman scores deviated and squared. So this will give you an estimate of how much freshman scores vary around that mean, right?
So would that be the answer to that question? What is the variance for just the freshmen? And that would be the answer to your question, and then take n-1.
So if you wanted to know the variance for the freshmen, that would be it.
Okay.
But you also want to know the variance for the sophomores, because you're not just worried about how much do freshman scores vary around the mean. You're looking at 4 groups at one time.
Right.
So you have to look at how do sophomore scores vary around the sophomore mean.
I guess that kind of throws. I guess I'll just keep listening.
No,
but I guess to me, when it says within, to me, that equation should just be for freshmen, because we are wondering within what is the variability.
Right, so you're wondering if freshman scores are more similar to other freshmen than to sophomores, seniors, and juniors, right?
I guess. To me, that's what within means to me.
Right. So you're looking at more than one group. So if you want to know if freshman scores are more similar within the freshman group than all the other ones. But you also want to know if sophomore scores are more similar within sophomore group than to every other group.
Okay.
And you want to know if junior scores are more similar to each other than all the others. So that's where it gets confusing. It gets very complicated because you're not just looking at one group, you're looking at 4 groups at one time. So this is the estimate of all of the within group variability. So that's why it's this huge, crazy, scary looking formula, because you're saying every freshman score minus the mean squared summed up. Here is part of the variance estimate for freshmen. But I also need to do that for sophomores. So I have to take all the 10 sophomore scores, subtract them from the mean for sophomores, square them, add them up. Then I've got one huge number that says this is all the variability around sophomore scores. I do the same thing for juniors. That's why you're so glad we actually aren't going to do these by hand. I'm not going to make you go through and do this. Just theoretically, this is what is happening. So you're getting that for each group, and then you're summing it all together. So that's why this is called the sum of squared error, because you're taking each group's variance and you're adding it together. So this number will be humongous, right? This is going to be a huge number. But it will tell you how much variability is within each group. And then you're adding it together. So you have one number. Does that help? I know it's a very it's a very confusing concept to wrap your head around, but that's what we're getting. So that's sum of squared error. So this will tell us how much each group varies within the group, and we're adding it together. So this is how much variability, like if we think about it in terms of like, if you look at the total amount of variability, if you look at all 40 people and their scores and how much their scores vary from a mean, this is how much variability is due to being within a group. This is how much they vary within their group. So that's one estimate, because again, we want to know whether being within a group makes you more similar to anybody else. So this is how much is the error there is in being a group, how much variability there is in a group. So this is one estimate we have to get. The other estimate we have to get, right, is the sum of squares between. And I have written in my notes here, this, okay. It's not too bad though. It gets a little bit more involved, but it's only because we have to introduce ourselves to this kind of new concept, this grand mean, which we talked about. This is the mean of the means, or it's the mean of everybody in the sample, regardless of group. So if you just took these 40 people and you got the mean of the 40 people, this is that mean. This is the mean of everybody, regardless of what group they're in. So for the sum of squares between, right, instead of looking at variability within groups, we're looking at variability between groups. So to calculate this variance, we want to look at how much each group mean differs from the total mean of all the participants in our sample, this grand mean. And so when you look at this bottom equation here, you'll see this x1, xt. Xt is the grand mean. That's the total mean. That's the mean of all 40 participants in the sample, regardless of the group. It's the grand mean, overall mean. So just like in the last example, when we get the variance, we look at how each individual varies from the mean of the group. Now we're treating the groups as individuals, and the mean as the mean of everybody. So instead of looking at how participant scores vary around the mean, now we're treating the groups like people. And so the group mean is like the single score for the group. And now we look at how the group means vary around the grand mean. So it's just a difference in scope. We're just kind of going up one level. And we're looking at means and how the means differ. So we're basically just doing that. So if you look at this scary equation, you can see that we take each group mean, right? So this x1, x bar 1, this is the mean of freshmen. And we're subtracting that mean from the total mean, the grand mean. And then we're squaring it. We're taking it times the number of people in that group. And then we're doing that for the next groups. So basically what we have to do is we take each group mean, right? X of 1, X of 2, X bar of 3, X bar of 4. We take those and we subtract them from the grand mean. Do that each time, then we square it because we're getting the variability around each mean from the grand mean. And then we have to square it because we're getting like the sum of squares. Then we have to multiply that by the number of people in our group. So that's what this N1 is, the number of people in freshman group, N2 is the number of people in the sophomore group, N3 is the number of people in the junior group, N4 is the number of people in the senior group, right? So we have to take these by the number of people in the group because that helps us account for possible differences in the number of people in our groups. So we're keeping this simple in our example. We're saying we have 10 freshmen, 10 sophomore, 10 junior, 10 seniors. But as you read in the yoga sample, people drop out. People don't complete their measures correctly. So you could start out with 40 people, 10 in each group, and you could lose somebody. Now you've got 9. And we have to account for that and equate it. And that's what we're doing when we're multiplying these by n. We're multiplying by the number in the group. After we do that, then we sum it all up. So here's your huge sums sign. So you're basically just doing this on a different level, right? You're getting the variance for group 1 around the grand mean, getting the variance for group 2 around the grand mean, variance for group 3 around the grand mean, variance for group 4 around the grand mean, then you're adding it all up. And so after we sum the squared deviations from the grand mean, we multiply that value by the number of participants in the group. After that, we sum those values up, and now you have the sum of squares between. This is this value that estimates how much variability each group has around the grand mean. So basically now what you have is two values, right? After doing all of this, you have two values. You have the sum of squared error, which tells you the amount of variability each person in a group has around that grand mean. And you have the sum of squares between, and this tells you how much variability each group has around the grand mean. So,
Sorry, how do you,
yeah.
and the grand mean is just all of the means together and divided, right?
Right.
So the grand mean is going to be the same to each. RT is the same.
Exactly. It totally is. So I think the way it helps me kind of think of it, and hopefully maybe this is more confusing, but I just think just like we take every freshman score and subtract it from the freshman mean, now we're taking the freshman mean score and subtracting it from the grand mean.
Mm-hmm.
And we're looking at how much groups vary around that whole mean. So we're basically looking at how much of the variability is there within each group, and we're comparing it to how much variability there is between the groups.
So there's one answer for the first one, and there's one answer for the second one.
You got it.
Okay. So the first one, it's going to be the same, like freshmen and it's all the same. So everybody's going to have SSEV. It's one flat number.
Right, exactly. So you get one number that sums up all the variance due to being in a group. How much scores vary within each group. How much they vary around being in a group. And then you're comparing that to this value that says this is the amount of variability there is between groups. So how each group varies around the mean for all the means. So it's weird. It's like it's a difference in scope. It's like zooming out a little bit. So here where you're zoomed in and you're looking at all the group differences, right, now you zoom out and you treat the groups as people and you treat their means as the grand mean. So you're really looking at how much does each, like if we get the grand mean, we're saying this is the mean of the means. This is the mean of all the groups, right? It's the mean of the means. Now you're seeing how much does each group mean vary from the mean of the means. How does it vary around if you put in all of them together? Does that, it's very confusing. I was like, we can't even start talking about this after last class.
Right.
Like, this is so, it's a lot to take in. Because you have, and again, the beauty is we will not do this by hand. It is a lot to calculate. But theoretically, like this is why SPSS is so awesome. It is doing that like this. It's like, I got it. Here it is. So, but that's basically, this is what this whole analysis is doing. It is comparing how much variability you have within your group to how much variability you have between your group to see if it matters that you're in a group. So we'll keep going with this. But so basically right now you have these two groups. So just kind of reiterate, after doing all this, we have this sum of squared error within groups. This tells you the variability each person has around, in a group, has around their group mean, right? Adding that all together. Then you have this sum of squares between, and this tells you how much variability each group has around the grand mean. So we're just zooming out and looking at that type of variability. And when you add the sum of squared error and the sum of square between together, you will get the sum of squares total. We won't do much with this, but just so you know, this is the total amount of variability in the entire sample. So how much each person score, regardless of their group, how much that varies around the mean of the whole sample. So we're basically like, if you were to take every person's score and take the average score for this whole sample, you get the mean of the whole sample. We can also think of it as the grand mean. What we've done here is we've divided that variability, like every person's score around that mean. We know that we have that variance estimate, right? All 40 people, the mean of all 40 people, we know the scores vary around that mean. All we've done is we've taken that variability around the mean and we have broken it down and assigned some of it to groups and some of it to between groups. Some of it within groups, some of it between groups. And that is why this technique is called the analysis of variance, because you're basically taking all of the variance that exists in a group and you're saying, if we grouped these people, like you're taking all the variance in a sample, and if we grouped these people, would the variance within a group differ from variances between a group? So you're just basically slicing that variance up and assigning it different ways. So we're here. We've done a lot of work. Sadly, we are not done yet. We need to convert these scores to a comparable metric. So you remember that in that variance formula, we usually divide by n minus 1, and I was like, oh, we're not doing that yet. We're just summing them all up. That's because like we still have to divide these huge equations by an n minus 1. The problem is that these are different equations. They have different things that you have to divide by. So basically the sum of squared error up here, this SSE, this will always be larger than the sum of squares between. And part of it's because like if you look at the formulas, you'll see that this SSE formula here, the number of variances included in this calculation is based on the number of participants in the whole sample, right? You're going to have 10 squared variances here summed up, 10 squared variances here summed up, 10 here summed up, 10 here summed up, right? Here you're only going to have one number, and then you're going to take it times 10. One number, take it times 10. So these are going to be different estimates, and this one is going to be much bigger. Sum of squared error is going to be much bigger. And so we need to divide these by different numbers to get them back to a metric where we can compare them, because otherwise this number is going to be huge and this number is going to be smaller, and this is always going to look like it's bigger. So we have to kind of compare them. So because each of these estimates is looking at a different type of variability, this is within group, so we've got 40 people, right? This is between group, we've got 4 groups. They have their own different degrees of freedom. So so here we go. Here's our degrees of freedom. So since the sum of squared error, this deals with the amount of variability within groups, the degrees of freedom estimate has to take into account how many participants are in each group and how many groups there are. So this is our formula for getting the degrees of freedom for the sum of squared error. And so you can see that we're basically saying number of people in the group minus 1 plus number of people in group 2 minus 1 plus number of people in group 3 minus 1 plus number of people in group 4 minus 1. And that's really tedious, but if you look at it too, you're basically subtracting 1 for each group, right? So the other really easy thing to do is just get everybody in the sample and subtract the number of groups. So K is the number of groups. So this formula just boils down to number of people minus number of groups. So you can either do it this way, or you can just say 40 minus 4, right? So 36. So the degrees of freedom here would be 36. Since the sum of squares between deals with the amount of variability each group has around the grand mean, its estimate for degrees of freedom only takes into account the number of groups we have. So this is just the number of groups minus 1. So the degrees of freedom for the sum of squares between is just K minus 1. So 4 minus 1 is 3. So we have 36 degrees of freedom for sum of squares error, 3 degrees of freedom for sum of squares between. So why do we care about degrees of freedom? Like the only reason we care is because we have to divide by them. So we just need to know what to divide each of these numbers by to put them on the metric that will allow us to compare them. Because the whole point of this is to compare within variability to between variability. And we can't compare them on that huge scale, we have to divide them by numbers so that we can compare them. So we're going to divide them by their degrees of freedom, and that will bring them to a similar matrix. I kind of feel like you're in the matrix. Right? I don't know what is happening. So the good news is that after we go through, the good news is that SPSS will always do this for us. But so you know what it is doing in the background. While you're on Facebook. So you have to take those SSE and that SSB, and you have to divide them by their degrees, their respective degrees of freedom. This will put the variance estimates on a similar metric. It will also convert these estimates to what's called the mean square estimate. So once you divide them by their degrees of freedom, you will get the MSB and the MSE, right? So the mean square error within groups is the MSE. I wish they would just call it MSW. MSE, the mean squared error between groups is this MSB. And so all you're doing is putting it on a different metric. That's all you're doing is dividing it by, 36 or 3. So 36 on the bottom, 3 on the top, and you're getting these values. And what's nice is once you get these values, these mean square estimates, these are the values that we use in the formula that helps us to get that ratio, that comparison of within and between group variability. So obviously to convert those, you just divide by degrees of freedom. Then, as you can see right down here, you've got this F value. This is the value we get just by dividing the mean square between by the mean square error, mean square within, basically. So once we divide those, we have our F value. And so this F value is giving you the ratio of between group variability to within group variability. It's answering this question, are the differences between groups smaller or larger than the differences within groups? Are people more similar within groups than they are between groups, or are they not? Is there no difference? Does it not matter if you're in a group? So remember, we kind of talked about this at the very beginning when we got down here, that if this variability doesn't systematically relate to group, then it basically means it doesn't matter if, group doesn't matter. It doesn't matter. There's no difference depending on grade. So this F value is finally what we are looking for, that ratio of within and between variability. So now that we calculated each type, let me go through all the steps that we did. We calculated each type of variability, the SSE and SSB, we did that. We calculated the degrees of freedom associated with these. We divided each of these things by its respective degrees of freedom, and that put them into a comparable scale. So we have our MSB and our MSE, and now we've calculated the ratio of within and between variability. Now we can look at this estimate for the ratio, and if I remember my ratios correctly, right, any number greater than 1 would suggest that the numerator is larger than the denominator, right? Right? If, right? If this is bigger than this,
2/1.
right, then this will be greater than 1. The only time this would be less than 1 is if this was larger than this. So if we want to say that the differences between groups are bigger than the differences within groups, we want an F value that's greater than 1.
Say that again.
Right? Okay, so if the differences between groups is bigger than the differences within groups, we will have an F value that's greater than 1. And that is the whole point of our question, is if we think that group membership matters, then we think that there will be larger differences between freshmen, between sophomores, between seniors. Then we think there will be bigger differences within groups, between groups, oh my gosh, bigger differences between groups than within groups. And so when we look at this ratio, we think that between groups differences will be bigger than within group differences, and so this value will be 1, or greater than 1, right?
So, sorry.
Yeah, no, that's
if
fine.
the between the top number is
Right.
greater than what?
Is if it's greater than this bottom number. If it's greater than within.
And that's what we want.
That's what
kind of
we're
looking for.
Exactly. Yes, that's
So
a
if it's
perfect
greater
way to
than
say it.
1, then that's going to give us a p-value that's significant. Most
No,
times.
that's the
Not
next
necessarily.
step. We have to check it.
Okay.
Oh, there's another step.
Lower.
Yes. But this will say if it's 1 or bigger, then we at least know. So if it's 1, right, then we're saying they're equal, right? If this is 0.5 and this is 0.5, we're
If f equals 1.
if f equals
Okay.
1, then this is bigger, or these are the same, right? The only time f equals 1 is if these are the same. If f is smaller than 1, it means this is bigger, right? We're dividing by a bigger number, so it would be smaller than 1. That would mean that there's more variability within groups than between groups, which would basically say group membership does not matter. People are highly variable in their groups, so it doesn't matter. But if this between group variability is bigger, we're saying that the differences between groups are bigger than the differences within groups, and that's what we want to see, or
I have
that's
a
what we think
question.
we're seeing. Yeah.
These values that we find, like the f and the t,
Yes.
and then there's a significance associated with it.
Yes.
Is a certain f always associated with a certain significance, or is it different from data to data? And like, is a certain t always associated with a certain p? Or is
Yes.
it different from data to data?
It's always the same.
Okay.
The only thing that makes it different is our sample size.
Okay.
And so that's actually what we're going to right now, if you guys are ready to go on. So this is our F. This is what we've been working for. And this will tell us if our differences, this will give us that ratio. Now we have to check and see if that ratio is different, if it's statistically significantly different. And what's nice is those F and those T tables that you have, the reason you have those stable tables in your book is they are always the same. The only thing that differs is your degrees of freedom. And so what's awesome is some really cool guy back in the, I don't even know, I want to say maybe 1800s. I don't know, when was probability theory done? They figured all of this out. They were like, here's this curve. This is what the normal curve looks like. Here's the percentages of people underneath these curves, percentages of scores under these curves. And then somebody sat there and they were like, what if we move this curve over a tiny bit and make it a little bit higher? Then they're like, here's all the probabilities underneath this thing. And they figured all of those out, and that's what that table is. It's basically saying, what if we move this over a tiny bit? Now this curve looks different. Now here's the updated probabilities. So let's go ahead, let's look at it. So let's talk about our F distribution, because that's basically what we're saying is when you take your T value and you compare it against a T table, it is telling you that the number, it's basically telling you the likelihood of getting a score that small or that big based on the people in your sample if that score doesn't exist in reality. If it's only part of your sample. We can forget all of this if we want to. We can move on to, but that's basically, when you're comparing it against this, you're comparing it against a probability distribution based on a T distribution, if you want to think of it that way. So, so the F distribution, like when you get an F value, you have to look at an F distribution. When you get a T value, you have to look at a T distribution. When you get a Z value, you have to look at a Z distribution. So they made all these distributions so that you can get this value and you can check it and see how likely it is that you got this value if it doesn't exist in reality. So how likely is it you got it in error? And that's why we're willing to say we're okay with a 5% chance that we got it in error. Like, we're okay if P is less than 0.05. But if P is greater than 0.05, we're like, that's too risky. We're not doing it. So that's where all of that is coming from. So luckily, we have used the T distribution before. We're a little bit familiar with that. The F distribution is a lot like the T distribution. So if you remember this T distribution, we started talking about it. We were saying it's like the Z distribution. What's great about the T distribution, though, is what? Do you remember what makes it better?
The larger sample size.
Yeah, it fluctuates on sample size. So it takes into account how small your sample size is, and it says, I know if it's smaller, it's probably going to be platykurtic, and it's going to change the percentages under here, and it corrects for that, and it gives you that in the probability table. So it's great. And so with fewer people, it becomes platykurtic, and with more people, it becomes closer to normal. And so the depth of the curve in the T distribution, the depth of the curve changes with sample size, right? You can see it right here. Now let's look at this F distribution, which is a little bit more complicated, but it also changes based on the number of participants you have in your sample. So here's our F distribution. You can see we have a few different curves here, and when you compare the F distribution to the T distribution, what you'll see is that instead of just getting more or less kurtotic, right, instead of just getting taller or flatter, it also becomes more or less skewed, right? So it doesn't just go up and down, it goes left and right. And so this F distribution, it becomes more or less skewed based on two things, right? So you have two things. You can go up and down based on the number of people you have. You can go left and right based on the number of groups you have. So the T distribution just looks at how many people you have. The F distribution looks at people and groups. So it's looking at two pieces of information here. And you can see that, like, if you look at this black line, the F distribution associated with 50 people and 50 groups. What is that analysis? The closer you get to having a similar number of people and groups, the more normally distributed it is, right? But basically, and you don't even have to know any of this, but I think sometimes it helps when you're like, what is this F value and why do I have to find a P value with it? Like, what is the point of this? The whole thing is you're getting this, and these distributions are based on all of these curves that are corrected and depend on how many degrees of freedom you have. So it depends on how many people and how many samples or how many groups you have. Yeah.
So you said the F distribution looks at people and what else?
And groups.
And groups.
So remember we were like, oh, you got to get the sum of squares, errors, degrees of freedom, and that's 36. And you have to get the sum of squares between degrees of freedom, and that's 3. Here you have, this is why, because you are going to get this F value and you're going to compare it against an F distribution, and you need to know the degrees of freedom associated with the number of people you have and with the number of groups you have, right? So our people degrees of freedom was 36. Our group degrees of freedom was 3. Thank you. K minus 1, right? And again, I don't know that you even really have to know any of this, but this is what we're doing is we are looking at this. So the T distribution just takes account degrees of freedom for the people in your sample, right? The participants, number of people. The F distribution takes into account degrees of freedom for the number of participants, degrees of freedom for the number of groups. So it's looking at N and K, right? If you want to think of it in terms of like our symbols. So again, I'm not going to quiz you on this, but just so you know, when we calculate a T value, right, we compare that T value against probabilities for P values in a T distribution, right? That's what we do. We look in the back of the book. Well, really, we just ask SPSS to do it. But you can look in the back of the book. They have that table, and you say, I know what my alpha level is. It's 0.05. I know how many people I have. So I look and I see if I have a T value that's greater than that cutoff, right? And if your T value is bigger than that cutoff, you are pretty confident that you got this value with less than 5% error, right? Or 5%. You're 5%, less than 5% sure that you got it and it doesn't really exist. So we do the same thing here with an F value. You have to compare your F value against the probabilities for P values in the F distribution. So you have to find the F value for a cutoff of 0.05 alpha level, right? So, oh, luckily, look, it's all 0.05. That's how huge the the table is huge. Did you look in the back of your book? It's like 4 pages, back and front. Like you have to like pull it out this way and look at it. So this is all just for an alpha level of 0.05. So we have to know our numerator and our denominator degrees of freedom. So if you remember, our numerator was MSB, right? Between. So SSB, the degrees of freedom with that was 3, right? So that's our numerator, right? So, wait, this is not our numerator. So 3 and 36 is cut off, but it's going to have to be bigger than like 2.9, probably like 2.7. Right? So if you have an F value that's bigger than this cutoff, it's significant. Right? So basically this whole thing was to show you like this F distribution is much more complicated. It's awesome. It takes into account a lot of pieces of information. And if you were to like, if society collapsed and you could save the world with an F test, now you can do that. Like you can be like, I'm going to get out my notes. And I'm going to calculate MSE and MSB and look at this cutoff, and I can do it. So theoretically, this is what is happening. I'm make sure I said everything I'm supposed to. Yeah. And again, we all survived this. We all went through it together. Now you know exactly what ANOVA is doing. So now we've gone all that theoretically. Let's get back to something concrete. Like, what is the answer? Did our groups differ? So again, here's our high school sleep study. We've got 4 groups of students, 1 group for each grade. We surveyed 10 students from each class. Here's the SPSS output you get for that. And this is what's kind of cool. We talked about all this stuff. Here it is. And I even put in the corner here. I didn't get it on the one that you have online. But since it like rewords everything. So you know that the SSE is your within groups, right? Your SSB is between groups, and your SST is your sum of squares total. But so you can see here, here's our SSB. This is the sum of squared error between groups, right? So that second huge calculation where we were like x bar 1 minus x bar t, where we took each group and subtracted them from the grand mean. This is that value right here, sum of squares between. And here's our sum of squares within, and this is where we took each freshman and subtracted it from the freshman mean and squared it and summed it up, and then we did the same thing for the sophomores and the juniors and the seniors. And I said that this would be a much bigger value because you have the variability for all 40 people, whereas with the between groups, you have the variability for the means, so you just have like 4 groups. So you can see that that's much larger. The within groups is much larger. And here's total. So if you add them up, this is the whole amount of squared error for the entire sample from the mean of the whole sample. And so we're just dividing it up. How much of it is between the groups? How much of it is within the groups? And here's our degrees of freedom, right? So we have 3 within group or between groups, 36 within groups. That's what we calculated in our heads. And here's our mean square, our MSE and our MSB, MSB. And you can see that this is just sum of squares between divided by its degrees of freedom is the MSB, the mean square between. It gives you that right there. And same with within groups. Here's your sum of squares. You divide it by its degrees of freedom to put it on a similar metric. And here's that. And then if you were to do this, if you did the ratio to get the F value, the 4.90 as the numerator and the 1.311 as the denominator, if you divided that, you would get this 3.7 or 3.737.
How come that is different than the table?
Oh, because the table is just how little it has to be.
Okay.
Yep, so the table is if it's bigger than this value, you're good to go. If it's smaller, reject.
Let's just give the exact.
Yeah, that's why SPS is way better.
Okay, so if you look at the table,
Mm-hmm.
because this gives you your significant level, how do you get from the table to a significant level?
Okay, so
And I know we're not using the table, but
just to know, yeah, no problem. Okay, so our F value is 3.73. So we know that. And so if we were going to look at the table, like we would have calculated that because we would have like, when I took ANOVA, we had to do these by hand. Like we would be like, here's the table. Luckily we had small sample sizes. But yeah, we would sit there and like do them by hand. And so you would create this table with paper and pencil and you would divide it and here's your F value. And so we have 3 and 36 degrees of freedom and here's our F value. If we went here, we would have to look 3 and 36, which isn't on here. But if it was, it'd be even smaller level because you're seeing that these numbers are getting smaller as we go. So for an F, to be significant at the 0.05 level, an F value with 3 and 36 degrees of freedom would have to be, let's say, 2.5. And ours is,
3.7.
so we're good.
Just has to be greater than
It just has to be greater than.
Okay.
So if
we
we,
don't get an exact, we just say
No.
that it's less than 0.05.
Exactly.
Our SPSS gives us an exact, but
Yep.
we're used to the table, we would just have to say less than 0.05. So
Right.
we wouldn't know the exact P value.
you got it.
Okay.
And now you know why, like APA style, one of the notations we use is P less than 0.05. And that's because we didn't have this technology. So it was just like, look at the table, and is it less than 0.05? All right. Now that we have SPSS, we can say P equals 0.02.
Okay.
But since we've all decided as a scientific community that 0.05 is our cutoff, it doesn't matter if it's 0.02 or 0.049 or 0.00007. It's all less than 0.05. So some people are like, why do we have to say P equals?
Does
Just-
it matter?
it doesn't matter.
Equals or P less? Okay.
No, it doesn't matter. In fact, some statisticians are just like, because there's 3 conventions. There's P less than 0.05, P less than 0.01, P less than 0.001. Those are the 3 conventions. And some people like to argue like, oh, mine's P less than 0.001. That means it's really significant. Not really. It doesn't really matter. If it's less than 0.05, we're good. And a lot of it has to do with your sample size. So, yeah.
Okay, so
Yep, let's go back
with
here.
our table, it is significant because we're at 0.02 for
Right.
the p-value.
Yes.
So that's saying that it is more significant between versus within.
You got it. Meaning that the variability between the groups is bigger than variability within the groups to a significant degree. Yeah. Yeah, so the variability between the groups is bigger than the variability within the groups to a significant degree. So remember we said if the F value is 1 or greater than 1, it means that it's bigger, that between is bigger than within. But the significance test is saying to a significant degree. And, oh man. So we did all of this awesome work. Do you remember what a significant F test with an ANOVA means? What does it mean? What is our ANOVA question even asking? It's just asking if what? If
Up to sleep.
it's just asking, is any group different than any other group? So if you want to say which group is different, this table doesn't let you know any of that, right? All it's telling you is like, there's a group that's different. Something's different. And so this is our red flag, or our red flag, that sounds bad. This is our green flag. That's like, go. All right. So, if you got a significant F test from an ANOVA, all you would say is that, like a significant F test indicated that there was a significant difference between groups. That's all you could say. So here's your F, and we'll see how we write it up. Because if you got a significant difference between groups, you would look, like, which group is it, right? Like, don't you want to know? We already know, right? We got a pretty good idea. So, yes, it tells you that there are differences, but it doesn't tell you anything about it. So here are the descriptives for your group. Your group's SPSS gives them to you. Yeah.
One question on that.
Yeah,
last
no
one.
problem
So
there.
if there was more difference within the groups,
Right.
would that F value then move down and line up within the group?
So, right, it would be like 0.99 and less is like, and it can get negative.
Okay.
So it would be
So
like,
it would be down on that second line, and then would that ever be significant?
so like second line, like,
Like I
Oh.
guess I'm thinking of it like how we did with Levine's test.
Right.
We either had to go
No.
across or we had to move down. Does the line matter here at all?
no, not at all. In fact, basically, if this is not significant, you're done. You're just like, nope, no group was different than any other group. Because it's basically telling you that group membership doesn't matter. That the variability within the groups is greater than the variability between the groups. So people are just, they vary. Doesn't matter what group they're in.
And that's going to happen if the MSE is greater than the MSB.
Right. Yep. That's exactly it. And so that's why I wanted to take us through all of that, because all you'll have to do for your homework is click these buttons and get this out. But now you'll know exactly what that means and why it means that. And it basically is saying it doesn't matter what group you're in, because scores within group were even more varied than scores between groups. Like freshman scores were so different from other freshmen. They were more different from other freshmen than they were like sophomores. Like it's weird to think, but it's basically groups doesn't matter. It doesn't matter. So if you did not get a significant value here, you would just be like, groups aren't important. You would basically just report there were no significant differences between groups. And that's that. So yeah, and ANOVA showed there was no difference between groups. Then you move on. You're like, study over. I'm going home. That is my thesis. Thank you. And then you just write about why you may not have found anything. But if you get the significance level, then you're like, okay, what is different? And so here's descriptives for your groups, right? And so whenever you do an ANOVA, you can say like SPSS, I want the descriptives, and they will give it to you. And so here you can see, and here's our means that we had at the beginning of this whole thing with the little bubbles and different colors. So here's our freshman mean of 7.8, sophomore 6.8, juniors 7.4, seniors 6.2. So here's all of our means. So now with these pieces of information, we basically know some of the groups are different. Here's the means, but I still don't know what is significantly different. But if you look at these means, what would you guess is different? Right? Seniors and freshmen, at least they have the biggest difference. I think at least they're different significantly from each other. So to figure out which ones actually are significantly different, you have to do these post hoc tests. It sounds so gross. It's like post hoc. I don't know. I don't know. I have this thing about spitting, so I'm just like, it's my own weird thing. So we have to do these gross post hoc tests. Again, at this point, I want to remind you, if you don't have a significant F, don't do anything. You're done. You can go eat dinner. But if you do have a significant F, you have to do this post hoc test to find out which one is where the group differences lie. And your book mentions a bunch of them, but we'll always do Tukey's. It's got the best name. It's called Tukey's Honestly Significant Difference. So you'll see it written up as Tukey's HSD. Like, Tukey's a great word. And then it's the honestly significant difference. Like, honestly, this is a significant difference. So this is the most commonly used one. We can just check a box on SPSS and it'll do it for us. So your book walks you through how to do a Tukey's honestly significant difference test and to get the value and to compare it against the table of critical values in Appendix F. We're not going to do that. Let's keep conceptual. So we know, like, if we get a significant F value, we have to do these post hoc tests. SPSS will calculate it for us. And so Tukey's test, what it does when you check that box in SPSS, it goes through and it does all those tests. So it's like, I'm going to compare freshmen against sophomores, juniors, and seniors, and I'm going to compare sophomores against freshmen, juniors, and seniors. And it does all of these tests and looks for these comparisons. So here is the stuff, this is the output you'll get when you ask for Tukey's test. So you can sleep down here, or you can sleep, you can see down here, it says sleep hours and Tukey's HSD. And so you can see that if you want to talk about these in row blocks of rows, you've got this freshman block. And you can see that that's what it's doing. It's got freshmen, and it's comparing against all other groups. It's got sophomores, and that block is comparing against all other groups. And you can see that in the mean difference, it's giving you the difference between the means, right? So it's saying that for freshmen and sophomore, there's a difference of 1. For juniors and freshmen, there's a difference of 0.4. And so it's doing that. So when you're looking at these, it's going to give you, for each of these comparisons, if you look all the way across, so let's just say freshman block. When we look at the freshman-sophomore comparison, your mean difference is 1. Here's the standard error associated with mean differences. Here is your significance level of that difference. So it's kind of like it's doing t-tests for every one of these things, right? So it's giving you, you will have a significance level for each comparison. And so if we go ahead and look down, let's look at freshmen. So the junior comparison, not significant. Senior comparison, what do we have here? It's significant, just like we thought it would be. So I'll put a little star up there. So that is telling us that the freshmen are significantly different from the seniors, right? That might be what's driving that significant F value that we got. And we'll go ahead and we can look through all of these. So freshmen, but you can see that the sophomore group comparisons, no significant difference, right? Junior group comparisons, no significant differences. This one's coming close, but it's not significant. Seniors, if we look at all the comparisons, what is significant here? Freshmen. But we already know that because we already looked at that. So you'll see that these tests are being repeated, but right there, that's the test that is significant. And so so once you get to this point, you have almost enough information to write up your test results, right? We know we've got a significant F value. There was some difference between the groups. We know that the difference is freshmen and seniors. The last thing we need to do to write this up is we have to figure out the direction of the difference, right? You want to know if the seniors were lower or higher. And so luckily, when you do an ANOVA and SPSS, it will give you descriptives also so that you can look at those means again, right? So when we look at this, here's the 2 means we're looking at, right? Because we know it's freshmen and seniors that are different. So if you were going to interpret this difference, what would you say? Like, who's bigger? Who's smaller?
Freshmen got more sleep.
Totally. That's exactly it. So this is exactly how I would write it up. There were differences in the amount of sleep high school students got each night. And so this is close to how we report our F values, or our T values, except for you'll see now instead of just having 1 degrees of freedom in parentheses, we have 2. So you have an F of 3 and 36 because you're telling them this is how many groups I had, this is how many people I had. Basically, minus things minus your N and K and all that stuff. So I would say there were, because you're basically saying, yes, there were differences in the amount of sleep high school students got each night, and now you're proving it. Here's my F value and my significance of the F value. And then I say specifically, freshmen with a mean of 7.80 and a standard deviation of this, freshmen got significantly more sleep than seniors. And here's their mean and their standard deviation. Alicia, I messed that up. That's supposed to be a standard deviation. But so it will look just like this.
So you don't put P.
Yeah, you would not put P. I'm sorry. It should be 7. It should be, I can change it right now. Standard deviation of 1.03, right?
You said that there was just that.
Yeah, you just put the P.
Yeah, sorry. There. What's that? Oh. Okay. There. Let me go back up here. Okay, so when you're reporting this, go away so I can, there, do this again. No. What is happening? There, okay. So this is how you would report it. Sorry.
So you just do your mean and standard deviation, and here's your test.
So it's this
Yeah.
the p-value from your from that p-value, not the 0.018
Right.
from the second chart.
Exactly.
From the
So
post
that's
hoc.
right. So you're reporting the F test. I'm glad you caught that
Okay, so
because
you
I wouldn't
report
have
the
even
F
thought to
test.
bring that up. You are reporting your F test because your F test is saying there is some significant difference. So that's why you're saying there were differences. Here's my F test to show you that. And then I just say, here's the differences.
And you don't need the P from the postdoc?
You don't.
Right.
I think if you had multiple group differences, you know what? No, you don't.
Because you already know, you're already saying there's a difference, and then you're stating which ones are different.
Exactly. Yep. That's what I would do yeah, just do it. That's exactly what you would do. All right. So just so you know where all this information comes from, where I got it from my write-up, here's your
ANOVA table that we looked at before with your F value right there, your P value right here. Here's your degrees of freedom, 3 and 36. So they'll always be organized like that. So it'll always be smaller and then bigger, right? Or it'll always be top and bottom. They might, I don't know if there's ever an instance where they're the same, but they're organized like that. So 3 and 36 equals 3.74 with the significance of either P equals 2 or P is less than 0.05, right? So just like this or just like this. And I'm sorry, so when you were writing an APA style, I've been trying to update all of these to match it, but it should only be 2 decimal places. If you did 3 or 5 on your homework today, it's not a big deal. There should be 2 decimal places, and weirdly enough, you never put a 0 before a decimal point. If there isn't a 0, a value greater than 1.
Right.
So, like for 0.05, you'll never, because we would never have a p-value of like 1.72. It will never be greater than 1. So it's really weird. So there's no 0.
Yeah, it's weird. And correlations, when we go through next, it'll be the same thing.
Is
They're-
that for all P-values, never put a 0?
I know, it's weird. Yep. It's newer or recenter, more recent. So there's no 0 before any.
In nursing school, I learned all my nursing students, I tell them to put a 0 because when you're talking about like milliliters of what are milligrams,
Yes.
because they say if you have like 0.15 of a medicine,
Yeah.
and you don't put that 0 in front of it, but if you miss it and you give them 15 milliliters, that's 100 times more.
That's
and it can kill
so.
them.
Yep.
Don't put a 0. Oh.
No, but you know what? And this is only the norm for values that can't be bigger than 1. That's it. And honestly, it's really,
So for P, just for your P value, you would never put a 0 in front of it. For your correlations, you'll never put a 0 in front of it. But for everything else, you could. Like a T, you could technically say, if this was 0.74, you could say 0.74 because it can be bigger than 1. But it's weird. It's this weird.
I learned it this summer. I was like, okay, I guess.
And you italicize the F and P.
Yep, you've got it. Yep. Italicize the F and the P. In fact, I think, yeah. So we don't have to walk through all of this because we've just basically been talking to it. But just so you know, it's written down for you in that slide. This is how you would report a one-way ANOVA, right? If it's not significant, just say it's not. No post-hoc tests. You don't have to report mean differences. It's not significant, right? And if it is significant, you need to specify what the groups are, mention what the variable they differ in, right? And provide the mean and the standard deviations for the group. And this says it there too. Taking that out of here. Anyway, okay. So, that was your one-way ANOVA. That was huge, right? The last thing I just want to kind of reiterate is the whole point in doing that is if you just did multiple t-tests, you would inflate that area. So it said, or that area, that alpha level error. So like it says here, each t-test result leaves some possibility that the null hypothesis could be falsely rejected. And when you're doing multiple t-tests, it's kind of adding that error together. And so each time you do a test, you're willing to accept a 0.05 error. But if you do 2 tests, now you're accepting a 0.10 error. 3 tests is a 0.15. 4 tests is a 0.20. And that's what would happen if you did, like, how many t-tests would you have to do? You'd have to do at least 11 or 12 t-tests to see all the group differences. That's 12 times 0.05. That's how you're inflating your error. And that's why you have to go through and do the ANOVA, because the ANOVA is what you could call a multivariate analysis technique. It considers multiple variables at the same time, and it keeps that alpha level in check. And so it's possible to get a non-significant F value and find group comparisons that are significantly different. But they don't count because your F value is it's actually kind of like bringing your P value down even farther so that you don't accidentally find a significant result that's not really significant. So sometimes they call it an omnibus test. That's why you have to do it, because you're taking care of that inflated error and you won't have to worry about it. But yeah, the take-home point is like, if you have more than 2 groups, you have to do an ANOVA. If you have 2 groups, I don't know why you would do ANOVA when you can just do an independent samples t-test, right? So if you have 2 groups, do that. If you don't, well, NOVA. All right, so this is my picture for you, because one of my students sent it to me over the weekend. I put the boy in there for you, Kelly, because I know you probably very much appreciate Ryan Gosling, but yeah, she sent this to me that when I run an ANOVA, the only thing significant I hope to find is you. So, all right, do you guys let's do like oh my God, it's 7:45. Let's do like a 10-minute break and then we'll do correlations, or do you want to just keep going, do correlations? I know, let's do it. Okay, correlations is way faster and easier. Yes. Okay. There is no way we could have done ANOVA last week. Like, oh my gosh, that's so much. Right? Like, it's hard enough to figure it out today. Can you imagine talking about that after Levine's test? You're like, no, you want it to be greater than 0.05. All right. So correlations, a lot easier than one-way ANOVA. They're common in social sciences research, so that's why you have to learn about them. Because we like using them when we can't manipulate or control a variable, right? Or we can't randomly assign people to groups. So we're kind of flipping here. Instead of looking at group differences, we're going to do a totally different thing where we're looking at relationships among variables, how similar variables are to each other. So instead of looking at how a nominal independent variable, like groups, will influence a scale-dependent variable, like hours of sleep, now we can look at how a scale-independent variable influences or relates to a scale-dependent variable. So correlations help us to assess the degree of relationship among 2 continuous variables. So no nominal or ordinal, we're looking at continuous variables, scale level variables. And so this is the first analysis we are looking at that lets us look at that, right? It's the first analysis that lets us look at 2 scale variables together. So it's great. It lets us answer questions like, is there a relationship between bad cholesterol and how much people exercise? Or is there a relationship between grades and how many hours people study for a test? And again, one of the great things about correlations is they let us look at these relationships without controlling or manipulating anything, right? So we don't assign people to different hours of study. We just take advantage of the naturally occurring variability in hours of study. And we just give people a measure and we say, how many hours do you study? And what was your test grade? And just by knowing those two pieces of information, we can look at a relationship between them. So it's you can see why people like using them. They're not that in depth. I mean, you can get right. They're not painful. I love them so much. They're like my favorite. In fact, my advisor, one of my advisors on my thesis committee and dissertation committee, he was like, if I was going to get a tattoo, I would get a correlation formula on my back, like a tramp stamp, which is a horrible word. I hate saying that word. But he's like, that's what I would get right there, because the correlation is the basis of like so many analyses. It's so great. So he really loves correlations. I'm going to go with him when that happens. Like, let's do this. We can both get them together. So it's great because all we have to do is measure these variables at the scale level and do it. And so, yeah, they take the variability, they take advantage of the naturally occurring variability in two different variables in our sample. So basically, what correlations are doing is they're looking at the scores in your sample to see if the variability in one score, like cholesterol, if the variability in cholesterol systematically co-occurs with the variability in another score, like exercising. So like systematically, do people who have higher levels of cholesterol tend to report lower levels of exercise? So like basically we know that some people will say they exercise more and some will say they exercise less. Some people will have higher levels of bad cholesterol, some people will have lower. And we're just seeing if this variability is related, systematically co-occurs. And so that's all we're doing. We're just looking for this relationship. So is it related in a systematic way? So the answer to this question comes in the form of a statistical test of the correlation coefficient. So we use a formula that helps us to compare the variability in both of these scores in a single value that tells us the strength and the direction of the relationship between two variables. So your book, as always, it likes to give you a lot of information. It tells you about all kinds of different correlations. But the most common is this Pearson product moment correlation coefficient. And so from now on, I'm just going to say correlation coefficient and pretty much know that that's the standard. Like anytime somebody says correlation, unless they specify otherwise, they're always talking about the Spearman one or the Pearson. Oh my gosh, sorry. Pearson product moment correlation coefficient. You know, the PMCC, PPMCC. Where we want to be. So the correlation coefficient, this is this number. It ranges from 0 to positive or negative 1. It tells you two things about the relationship between two variables. It gives you the direction of the relationship, right? Positive or negative, and it tells you the strength. So the direction is given by the sign, positive or negative. So positive coefficient tells us that the variables move in the same direction. So as one variable increases, the other increases, like hours of study and test scores. Or as one variable decreases, the other decreases. So again, hours of study and test scores. Less you study, lower your test score maybe. So it's important to recognize that lower with lower or decrease with decrease, that is not negative. It is a positive direction because it's saying they both go in the same direction. A negative coefficient tells us that the variables move in opposite directions. So negative stands in for inverse relationship, right? So as one variable increases, the other decreases. So, and as one variable decreases, the other increases. So a negative relationship is one like cholesterol and exercise, right? The more you exercise, the less your cholesterol is. It's an inverse relationship. That's what the negative sign is saying. So it is totally fine to have a positive correlation that has two scores decreasing at the same time. If they go together, it's positive. If they go opposite, it's negative. Okay, so direction is given by positive or negative, right? Strength is given by the actual number. So the closer the coefficient is to 0, the weaker it is. It's basically saying there's 0 relationship, right? 0 is weak. The closer the coefficient is to 1, either positive or negative, the closer it is to 1, the stronger it is. 1 is the highest it can go. If you have a correlation over 1, you have a problem. It can only go to 1. So again, the negative coefficient does not mean it's weaker. It only tells us the direction of the effect, whether it's inverse. The strength or the weakness of a correlation depends on the number regardless of direction. So a correlation of negative 0.75 is stronger than a correlation of positive 0.03, right? It's the bigger the number is, regardless of sign, is stronger. All right, so let's look at a couple of examples of scattergrams, as your book likes to call them. I've always heard of them being scatter plots, but scattergram is a really cute word. So let's go ahead and just interpret a couple of correlations. And so while we walk through this, let's say we're looking at test scores and hours of study, right? We've been kind of talking about that. A correlation means that there is a relationship between these two things. Correlation. It's a relationship between two things. It's nice. It's even in the title. So you can see test scores here on this y-axis, right? Going from low at the bottom up to high. And you have hours of study here on the x-axis, right? Going from like 0 hours of study over here all the way to like, I don't know, let's say 50. Got some really study happy people. So basically each point here represents a relationship between those two things, the scores for both of those things together for one person, right? So let's say here we've got somebody who studies 3 hours a week and they have really low test scores, right? And up here you've got somebody, this data point represents really high hours of study and really high test scores, right? And so you can see you have this correlation coefficient here. It says it's +1. So does anybody want to interpret what this correlation between these two variables means?
The variables move in the same direction.
Right, exactly. So it's basically saying higher hours of study, more hours of study is associated with higher test scores. Fewer hours of study are associated with fewer test scores. Moderate is associated with moderate. So they go together, right? So that's a positive correlation. Let's go ahead and look at what a negative one looks like. So again, here we go. We have bad cholesterol on the y-axis, so it's going from low to high. We have hours of exercise here on this axis going from low to high. And here a data point represents everybody's score on two variables, right? So you got high exercise here associated with low bad cholesterol. Low exercise here associated with high bad cholesterol. And here's our negative coefficient saying that this is a negative relationship. So does anybody want to interpret what that means?
Hours of exercise increase, cholesterol decreases.
Yeah, exactly. So it's just opposite relationship. So again, I always have to point out, because I will definitely have a question on the quiz that has a large negative correlation and a small positive correlation, and it's going to ask you which one's stronger. And it's going to be negative. It's going to be about the number, not the sign. Because people always get tripped up by that, and it's so important to remember. Negative and positive only tells you if they go together or go opposite. The strength is given by the number, and you'll be able to see this by like a correlation of 0. So here we've got height, right, from bottom to top, so low height to high height, you get taller. And here you have intelligence going from low to high. And so these dots represent people's score, right? So here's somebody who's kind of short, and they're moderate intelligence. Here's somebody who's really short, and they're really low intelligence. But you also have somebody here who's short, and they're really high intelligence, right? Like if you were going to try and draw a line in here, where would you be able to draw it? There's not really any relationship, right? I mean, like everything's just kind of scattered all over the place. Like you couldn't do a nice line here, or here, like a line would fit anywhere. And so this is what it would look like if you have a correlation of 0, right? They're all over the place. There's not really a systematic relationship between intelligence and height. So the correlation is 0 because there's no relationship. It's 0. It's very weak. There really isn't anything. So again, remember, the closer it is to 0, the weaker it is. And the closer it is to 1, the stronger it is. In fact, these are perfect correlations. They're not in real life, but like this is what a perfect correlation would look like. Straight line. Okay, so yeah, so we know how to interpret correlations. Let's look at how we calculate them. And we'll walk through this a little bit faster because it's a lot easier to understand and there's a lot fewer things that you have to do. Yeah, many fewer. Anyway, so SPSS also will always do this for you, so it's very nice. Again, thank you, SPSS. But again, as long as you had z-scores and the table, you could do these like in your backyard if you wanted to on paper and pencil. So you can see the formula here, and you can see that to get the correlation coefficient, the first thing you have to do is get standardized scores, or z-scores. So when you look at this R equals the sum of z of x times z of y. The z means the z-score for x and the z-score for y. So that's what the z stands for. And so, for example, if we're looking at the relationship between hours studied and test scores, the first step in finding the correlation coefficient among these two variables would be to get the z-scores for both of these variables. And since we're pretty sure that hours studied is causing test scores, right? It's not that test scores are causing hours of study. What is hours of study? Is that our independent or our dependent variable? We think hours of study is causing test scores. Right, it's the independent variable. And I don't know if you were familiar with this, but another notation for independent variable is x. We think x causes y. So another notation for the independent variable is x, and then the notation for the dependent variable is y. And in our study, what is the dependent variable? Yeah, test scores. Totally. So that's what this x and y is. So you're getting the z-score for the independent variable, which is our study, and the z-score for our dependent variable. And that's, you can see I've done that right here. So if you look, you've got hours studied, here they are. Here's grade just for 3 people, because, I've done these by hand too, and it gets crazy. So I just had SPSS calculate the z-scores for me. So now I have z-score for hours study, z-score for grade. And remember how to interpret z-scores, right? Do you remember that positive z-scores indicate that it's above the mean? Negative z-scores indicate that it's below the mean, right? So we've got this person here. They study a larger than average amount of hours study, right? They're above the mean, and they have a larger than average grade. And then you've got this person way down here who studies 2 hours, has a grade of 78. They have a lower than average amount of hours that they're studying and a lower than average score on their test, right? So it's just important to remember what z-scores mean while we're kind of going through this stuff. All right, so that's the first step in doing this equation. You have to get these z-scores. Then if you can look at the equation, what is it asking us to do with them? Yeah, multiply them. So for each participant, you have to get what's called the cross product of the z-scores. So you're basically getting, it's called the standardized cross product. And you have to get them for every individual for both scores, right? So you can see that's what I'm doing up here. So here's our z-scores. If I took these two, this 0.775, and took it times the 0.577, I would get this standardized cross product for this person. And then I have to do it for the next person and the next person. You do it for everybody in the sample, right? Oh, good. Really awesome. Okay, cool. So now you have, for each person, you have the standardized relationship among the two variables for each person, right? So now all the variables, all these values are on a more standardized, more similar centralized metric, right? So instead of being all over the place, they're really close to like 0 and 1, right? They're between 0 and 1 for most of the part. And so multiplying these values together provides this information for each person regarding the relationship among the two variables of interest. So really all you're doing is taking the hours they studied times their grade for each person. The only thing we're doing different is we're putting it on the z-score metric so that the numbers are closer to 0 and 1, right? So they're smaller. So again, at this point, think about what z-scores mean and how multiplying them would influence the numbers that you get. if you have a positive z-score here and you multiply it by a positive z-score here, you're going to get a positive integer, right? If you have a negative z-score here and a negative z-score here, you're going to get a positive integer. And that's why positive just means they go together. It means negative with negative or positive with positive, right? So multiplying these together, this top row here, we're basically saying if you have a higher than average time of studying, you also are likely to have a higher than average test score, right? That's what this value is telling us. And same down here, if you have lower than average hours studied and we're multiplying by lower average grade, you're going to have a positive correlation as well. So it's basically just taking your standardized z-scores and multiplying them together so that you get this relationship. So, because it's not about positive and negative, it's about, are these things systematically going together? Does negative go with negative? Does positive go with positive? And so in contrast, like if you had a negative and a positive, right, that would give you a negative number. If you multiplied a positive by a negative, you would get a negative number, and that would shift. So that's how we get our correlation values. So basically you have to get this standardized cross product. That's what this means here. The standardized cross product for each participant. And then you sum these up, right? So you add them all together and you get this value. This is the sum of the standardized cross products. That's what this is right here. So we've done that. And this will give you this one number that summarizes each individual's relationship between the variables, right? So this one number is saying, this basically is tallying the relationship between the variables for everybody. It's meaningless, like it doesn't make much sense when you interpret it, but that's what it's doing. And then the last thing you have to do is divide by n. So if you divide this by n, this will give you the average standardized relationship among the two variables for the entire sample. So you're basically describing what the relationship looks like for everybody in the sample. And so here is that number right there. So again, kind of like your book says, you're not describing the relationship for one person. You're describing the average relationship, the average standardized relationship. All right, and so here is our correlation. It's a 0.65. Does anybody want to take a stab at interpreting what that means? It's a correlation of 0.65. But
I was just going to say there's a stronger relationship. It's closer to 1.
right, awesome.
And it's positive.
Right, meaning
As you study more, your test scores are higher.
right. Or if you study less, test scores are worse. So that's it, right? That's so much easier than an ANOVA. It's close. So just to kind of reiterate, when you're calculating it, this is all you have to do. You convert scores for each variable to z-scores. For each participant, you multiply those together. Then once you've done that, you add them all up, and then you divide by the number of people in there. That's how you get your R. So it's nice and easy to get the R value. So again, like everything else, we've got the correlation coefficient, but now we have to see whether it's statistically significant, right? We have this value. Did we get it by chance, by aspects of our sample, or is it a real value? Is it reflective of what happens in the population? So to put this in terms of null hypothesis significance testing, your null hypothesis is that there is no relationship. So this weird looking thing here, this is called rho, and it's basically the population correlation coefficient. So our null hypothesis says there is no relationship between the variables, right? That the population correlation is 0. And our alternative hypothesis is that it's not 0, right? That it's right, that is greater than 0. It might be weak, but it's not 0. There is a relationship, exactly. And as usual, we know that to test our hypotheses, we have to calculate a test statistic and compare it against a distribution that has these preset alpha levels, right? Does everybody want to know the good news? It's a t-test. So we don't have to like learn a whole new distribution again, like the F one. It uses our favorite little t distribution. And so to find out if our correlation is significant, we just have to do this t value. So we take our correlation, we subtract from it the population correlation, and we divide it by the standard error for the correlations, and that would give us the t value. We are not going to do that because SPSS will do it for us, but that's how we get our t value for it. So again, it's just kind of important to know that the correlation coefficient, it tells us this average standardized relationship among two variables for a group. After we calculate this value, we have to test it for significance. And the way that we do that is we would calculate this t value based on our sample and comparing it to the population and dividing it by the error we would expect to have in our sample, which is similar to what we would do for our t-test as well. So this is exactly what SPSS has done here. So you can see we have descriptive statistics, descriptives. It gives you, like usual, the mean and the standard deviation for our variables. So you can see the mean. There's the standard deviation. Test grade, the average test grade is 87.2. So you can see the mean and the standard deviation. You can also see the number of participants for each variable. So we have 20 people who gave us information on both these variables. And then you can see down here, this is the correlations table. And so the correlations table is organized a little bit differently, right? Like it's weird. So basically, it gives you the variables on both ends. So you have hours studied here, test grade here, going down, and then going across you have hours studied and test grade here. And what you're looking for is the intersection of these two. It's because it's trying to tell you about the relationship between two variables. So it's telling you test grade is related to hours studied right here. So you look for their intersection. This is giving you the correlation between hours studied and hours studied, which is perfect because it's the same variable. Like, you don't really care about how hours studied relates to itself. You would expect that it relates perfectly because it is itself. So what you want to see is you want to go to where they intersect. You can either go across this way. You'll see it's a mirror image. It's so when you look at hours of study intersecting with test grade down here, it's the same as when you look at it over here. It's just the intersection, either way. And what you're looking at here, what you can see is that this top row, study hours, it gives you the Pearson correlation. Study hours with test grade, the correlation is 0.655, right? Below that is the level of significance. So it tells you sig two-tailed. If you go all the way across, it's 0.002. So it's significant. And then below you can see the number too if you want to see the sample size. So we know we have a correlation of, we basically calculated that a second ago, right? We looked at our correlation was, I don't know, there it is. Yep, 0.651. I did that with only 3 of the people, but if we use all 20 people, we see that is basically 0.655. So if you want to interpret this one, it's basically the same, right? Hours of study, as hours of study increase, so do test grades. The unfamiliar thing with this kind of test is we're missing some information, right? Like we have no t-value, there's no degrees of freedom, like we know that this stuff got calculated to give us this significance, but we don't care. Like SPSS doesn't give it to you, APA style doesn't have you report it. It's you basically say, here's my correlation and here's the level of significance. So SPSS is like, you don't even have to care. And that's also why I didn't have you go through and calculate it, because you don't even report it. If I was going to write this up, this is exactly how I would write it up. Hours studied was positively correlated with test grades. Give the correlation rounded to 2 decimal places. Either give p less than 0.05 or give the actual level of significance up to 2 decimal places. You can also do 0.001 if you want. It's so weird. So you can always just do 0.05 and not have to worry. So I say that it was positively correlated such that greater amounts of time spent studying were associated with higher test grades on average. Or
lesser amounts of time studying were associated with lower test grades on average, right?
It's positive, so they move in the same direction.
And we said our study was positively correlated with test grades because of just initially looking at the correlation coefficient.
Exactly.
And then what is the significance of the R?
Like where did it come from, or?
I don't know.
So yeah, basically
I know where it came from, but it's just
yeah. Anytime you calculate a value, you have to test it for significance. So you can calculate the value and you're like, that's great, but is that just because of our sample, or what percent, like how sure are we that this is a sample statistic that represents the population parameter? And so like right here, it's basically
kind of like when we list our t-test.
Yeah, you don't have to list it. It's crazy. Like it's
in the last lecture we listed a t-test.
Yes.
Yep, and you don't, it's so weird, you don't have to. So SPSS is calculating this t-value, and that's what the level of significance is based on. But it's just like, it just tells you.
This is it. That's all you care about is, here's my my correlation coefficient, and yes, it is significant. In fact, it even stars it for you. It puts little stars on it. It's like 1 star means it's less than 0.05, 2 stars means it's less than 0.01, and it tells you that down here. 2 stars. Yeah. So it's saying, like, we really don't care about the t-test. So it's weird. That's why I was like, the unfamiliar part about this is there's no t-table, there's no degrees of freedom. You don't write any of that up. You just get the correlation and the level of significance, and you interpret it.
And that's it.
So the significance still comes from a p-value. I'm just having
Yes, it does. So it comes from this thing. So you would calculate this t-value
to get what?
to get the t-value associated with your r value. I know, right? And then you would compare it against a t-distribution with a certain number of degrees of freedom. But you do not have to do that. It's weird. You don't even care. So it's weird because it's like every other thing we've ever done. Like you get like a t-value, and that t-value gives you a ratio of your group to the other group divided by the error that you would have. And then you get that t-value and you compare it to a t-distribution. And you say, like, I have to have this level of t before I'm willing to accept this is okay. It is doing all of that for you behind the scenes. It's really weird. So it's doing it.
But the hour study was positively correlated. That has everything to do with what the coefficient was from step number 1.
Right. Yep.
Okay.
And it's funny because you won't even do any of these steps. SPSS will do it all for you. All you will say is, give me the correlation between hour study and test grade, and it'll be like, here you go. Here's the correlation, and here's the significance. And if it's not significant, then you're just like, they weren't related. That's why I'm like, these are so easy. It's like deceptively easy. All you care about is the R and the P. And SPSS is even like, it's significant. Like, you wouldn't even have to look at P. You're just like, no stars, never mind.
Yeah, it's that simple. So when you're writing it up, that's exactly what you do. You interpret it based on this R. So we're not looking at group differences. We don't have to look at descriptives. All you are like, is this R, is it bigger than, is it closer to 0? Is it positive or negative? That's it. So you're like 0.66, that's a pretty good number. And it's positive, so they go together. So you just write that it was positively correlated, and what variables you're talking about, hour study, test grade. Then you put those information in parentheses, and then you interpret it really quickly. You could say decrease with decrease, you could say increase with increase. If it was a negative correlation, you would say increase with decrease, right? You would be inverse, but that's all you do. And then, like, here's little things to remember. R and P are italicized. You have to report the numbers to the second decimal place. There's no 0 in front of the decimal on these because R can't be bigger than 1. So it's like there's no point. There would never be anything before the decimal place. Same with the P's. It would never be bigger than 1, so you won't put a 0 in front of it either.
Then you give the direction of the correlation and interpret what that means for the sample on average, right? All right, any other questions on that? We just have like 2 more things to cover about correlations. They're so awesome. They're very cool. So as far as correlations go, we have a couple rules of thumb for how strong they are. Like your book mentions, a correlation below 0.2 is considered weak. A correlation between 0.2 and 0.5 is considered moderate. And a correlation greater than 0.5 is considered strong. It's nice to know, but there's actually a really easy way to figure out how meaningful your correlation is. And it's by getting this coefficient of determination. And all you have to do to get that is square your correlation. And then you interpret this squared correlation as a percentage. So let me backtrack a little bit so this makes sense, right? When I was first talking about these correlations, I mentioned that correlations take advantage of variability, the natural variability in scores in our samples. And so when we compute correlation coefficients, we're looking at the scores in our sample to see if the variability in scores for one variable, like our study, see if that variability systematically co-occurs with the variability in another variable, like test grade, right? We want to see if this variability relates to one another. So we know that in our sample, the variable test grade, this varies, right? People get different grades on their tests, and we're thinking that maybe one of the reasons that they get different grades is due to what? Right, hours studied. And so we measured hours studied. But we know that hours studied also varies, right? I mean, we're kind of banking on that, right? Like not everyone is going to spend the same amount of time studying. So we're asking whether or not different hours of study might help to explain people's different grades. That's all. So we're looking at this variability and seeing, so like another way to say it is that we're asking if the variability in hours studied will help us explain variability in test grades. Right? So we're just looking at that overlapping variability. And we started answering this question by using this correlation coefficient. It helps us compare the variability in both of these scores in a single value that tells us the strength and the direction of the relationship between 2 variables. So the correlation coefficient is awesome. And if we just square this value, we get a value that tells us about explained variance, or the percent of the variance in one variable that we can explain by knowing the value of the second variable in the correlation. So let me say it like this. So like simply put, right, if we know that 2 variables are related and we have a measure of how much variation in one score is related to variation in another score, like if we have a correlation, we know how related they are, we can use that information to predict or explain the scores in the other variable. So we can use what we know about one related variable to help us understand another scores on another variable, right? Like if we know hours studied and test grade is related, and we know how many hours you study, it can help us understand what test grade you will get, right? Or the type of test grade you'll get. So to better understand this, imagine that variability in test grades is represented by this orange circle. So here's this test grade represented by this orange circle. Inside of this circle is 100% of all the different reasons why people get different test grades, right? So all the different reasons people get different test grades is represented by this circle. What we're trying to do is kind of chip away at this 100% to explain some of it. So we want to explain some of the variability in these test grades to explain reasons why people get different test grades. So here's all the reasons, all the variability. We're trying to explain some of it. And as we've said before, we think hours studied might help to explain these differences, right? We think that they're related and it'd help us to explain it. So when you look at this green circle, you can kind of imagine that this represents hours studied, and this circle represents 100% of the variability in hours studied, all the reasons people have study different amounts of times.
and we have a correlation between them. We know then that variability in grade and variability in hours studied is related. We know they're related. And so you can think of that correlation as overlapping variability. So right here, this is their overlap. They're related, they intersect, this is their overlap. This is the variability that these two scores share. So what we're looking at with the coefficient of determination is this percentage that tells us how much variability in test grades is explained by how many hours people study. How big is this overlap? How meaningful is this relationship? And so to get this value, all we have to do is square the correlation coefficient. So the correlation coefficient is 0.66. If you square that, I already did it, so I'll show you. You get 0.44. I updated it, I rounded it, so I think yours say like 3 digits, but I was like, oh, we'll just round it with the 2 decimal places since APA wants 2 decimal places. So our correlation coefficient was 0.66. If you square that, you get a value of 0.44. If we read that as a percent, that means that 44% of the variance in grades is explained by the number of hours studied. So 44% of the reason people get different test grades has to do with how much they study. And that's what the coefficient of determination tells us. It tells us how big of an effect, basically, our correlation has, right? Like 44%, that's a huge deal. 44% of 100 is just due to how many hours people study. So that means, like, if somebody had a bad grade, maybe one of the first things you would tell them to do is to try and study more, right? Because that will explain 44% of the reason they're not getting good grades. So that's awesome. It also means that there's 66% unexplained. So there's a whole other 66% of reasons people get different test grades. But we, with one variable, said 44%. And what's awesome, we won't do it, but with regression, you can start adding more and more and more variables into this to see how much more you can explain. So you can start looking at the relationship between like 8 variables at a time. Are there any questions on this so far? Like, I don't even know what you're talking about anymore at this point.
Not the easiest part of it.
Right?
But
Correlations
I
are
know I
awesome.
might be dumb, but 42.9%, how did you get 44 when you just rounded it?
Yeah, sorry. So I rounded the correlation to 0.66
Oh,
instead of that 0.655.
okay.
And so when you take 0.66 times 0.66, you get 0.44 instead of 0.429.
Okay.
Yeah.
All right. Yeah, I'm just wondering.
No, I'm glad, because that way you'll have it on Integrity, because I know it's like, and I can upload mine again too, but okay. So are there any other questions on correlations? They're so much easier than t-tests. It's almost ridiculous. So last couple of things to know about correlations then. They're only accurate if your variability has variation. So if the scores in your sample don't vary much, there's not variability to take advantage of, so it can't take advantage of the variability in the scores, and it won't be able to detect a relationship. So basically, like, if you have some reason to suspect that this variable should be related, and you collect data and you measure it, and you look for the relationship and it's not significant, look at the variability of your scores, because they might be restricted. It's a phenomenon called truncated range. You might not have much variability. Like, this kind of stuff happens when we measure positive things. When you ask parents how good they are as parents, nobody is like, I am a horrible, awful parent. You get all these scores on one end, right? Like, everybody is a great parent. And so when you try to relate how good of a parent you are to anything else, it doesn't show a very strong relationship because there's not much variability. Every parent, like, there's not a relationship to find. And it's not because being a good parent isn't related to all kinds of things. It's because when we measure it, all the scores are all up at the high end. So if there should be a relationship and you're not finding it, check your scores, because they might be restricted. So yeah, I found an awesome picture about this little box robot who wants a significant relationship, but his scores are truncated, so he can't find it. Anyway, all right, and so the other thing to be aware of is a curvilinear relationship. So correlations are designed to look for a linear relationship, right? We saw them through our scattergrams. It's trying to fit a line into these points. And if it's a curvilinear relationship, it's really hard to fit a line to it, right? So your book is a great example of math tests and anxiety levels. So you can see that with a little bit of anxiety, the scores actually start going up, probably because you're motivated to study, you're really hyper aware during the test, and so a little bit of anxiety actually increases math scores. But you also see that for like the last 30% of scores, too much anxiety really starts to interfere with your ability to perform. And so this is a curvilinear relationship. It goes up to here, but then it comes back down. And if you tried to find a correlation in this, it would draw a line here. It would tell you, right? Because, if you're trying to fit a line to this, that's probably the best place for it. And if it's a straight line. And so it would tell you there's no relationship, right? This is flat, it's 0. But there is a relationship, it's just not linear. So again, if you think there should be a relationship and you're not finding one, check to see if you might have a curvilinear relationship. Then you need a whole different test. So those are just a couple things to remember. And then last but not least, correlation is not causation, right? At this point, we always like to bring up the strong positive correlation between ice cream sales and crime rates, right? And it's probably not that ice cream is causing crime, and it's probably really not that crime is causing ice cream. Although I do kind of like the idea that like a bunch of criminals were like celebrating this awesome heist, so they all go get ice cream. So high crime rates cause that. But most likely there is some third variable driving both of them, right? And so usually it's like as temperatures rise, people leave the house more, they commit more crime, and they also get more ice cream. So that's it for the correlational design. I put this up here. Like I said, correlational design has to be used with scale variables. If you don't have scale level variables, you could still do a correlation. So that would fall under the purview of non-parametric statistics. You'd use Spearman's Rho. Your book says more about it. We are not going to learn it, obviously, but there it is for you. All right, any questions on any of that? It is 8:30, so this is what we can do. I was going to do like a experimental thing where I just gave you guys the lab and let you work on it, and I'm here for you. And I wasn't sure if maybe that would help you like do more hands-on stuff. So what we could do is end class, and you could work on the labs yourself, and you could email me and say, I'm freaking out, I can't do this, and I want to come and see you next Thursday, and I'll meet you here, and we can do that. Or we can go through it.
Is it something that you think that would be a bit more challenging that you could take it sometime? Or if you think that it's no different than anything else we've already been doing, it's simple steps, then let's just say.
I could totally Tegrity it, actually.
Is it more difficult than what we've already done with
It's
SPSS?
a bit more, let me see, it's a bit more difficult, but if you look at the lab, I don't know how many of you actually look at the lab because we basically walk through it. Okay, cool, because it will say step by step exactly what you have to do. And so
That's perfect.
yeah. So, and like I said, it says chi-square, don't do chi-square. You don't have to do it. So if you want to stay, I will gladly walk you through this. If you want to go, you get your lab points, you're fine. And if you're doing it on your own and you're like, I'm just still lost, especially in regards to correlations, then email me and we can either set up a time or we can Skype or I can walk you through it on the phone too.
Do you only need to hear from us on the lab if we have have trouble with it, or do you want us to send you something to show you
No.
you did it?
No, because basically the lab just walks you through so you get practice to do the homework. So as long as you've walked through it there, I'm fine with it. In fact,